Welcome all of you. I am Vishwas Khare from SSR College Silvassa. In this tutorial, we'll learn about necessary and sufficient condition for subspace of a vector space. Recall definition of subspace. Let W be a non-empty subset of a vector space V. Then W is called a subspace of V if W is a vector space under the same operation of addition and scalar multiplication as in V. That is, a non-empty subset W of V is called subspace if W itself is a vector space. Theorem. State and prove necessary and sufficient condition for a non-empty subset W of a vector space V to be subspace of V, or a non-empty subset W of a vector space V is a subspace of V if and only if the following conditions are satisfied. First, if U and V belongs to W, then their sum U plus V belongs to W. Second, U belongs to W and alpha is a scalar, then alpha into U belongs to W. That is, in this theorem, we have to show if W is a subspace, then these two conditions are satisfied. Conversely, if these two conditions holds, that is, if U and V belongs to W, then their sum belongs to W, and if U belongs to W and alpha is a scalar, then alpha into U belongs to W, then W is a subspace. Proof. Let W be a subspace of V. Then, by definition, W is itself a vector space with the operation as in V. Hence, condition 1 and 2 are automatically satisfied. Conversely, let condition 1 and 2 are satisfied. Then we have to show that W is a subspace of V. That is, to show W is itself a vector space with the operations as in V. First, if U and V belongs to W, then by condition 1 we have U plus V belongs to W. Hence, closure property of plus holds in W. Second, if alpha is a scalar and U belongs to W, then by given condition 2 we have alpha into U belongs to W. Hence, scalar multiplication holds in W. Third, taking alpha is equal to 0 and U belongs to W be any element, then by given condition 2 we have alpha into U is equal to 0 into U is equal to 0 vector which belongs to W. Hence, 0 element exists in W. Fourth, take alpha is equal to minus 1, then for each U belongs to W, by given condition 2, we have alpha into U is equal to minus 1 into U is equal to minus U belongs to W. Hence, every element in W has its additive inverse. Now, as the elements of W are elements of V, and they satisfy all remaining properties of vector space in V, so they satisfy in W also. Hence, W is a vector space, so it is a subspace of V. Theorem. Now, the previous theorem can be written in this form also. A non-empty subset W of a vector space V is a subspace of V if and only if the following conditions is satisfied. If alpha beta are scalars and UV belongs to W, then alpha into U plus beta into V belongs to W. That is, if W is a subspace, then this condition should satisfy, that is, alpha into U plus beta into V belongs to W. And conversely, if alpha into U plus beta into V belongs to W, for every scalars alpha beta and for every vector UV belongs to W, then W is a subspace. Proof. Let W be a subspace of V. Then W is itself a vector space with the operation as in V. Hence, given condition is automatically satisfied. Conversely, let given condition is satisfied. We have to show that W is a subspace of V. That is, to show W is itself a vector space with the operations as in V. First, if UV belongs to W, then take alpha is equal to 1 and beta is equal to 1 in the given condition. Then we have alpha into U plus beta into V is equal to U plus V belongs to W. Hence, closure property for plus holds. Second, taking beta is equal to 0 in given condition, we have alpha into u belongs to w. Hence, scalar multiplication holds in w. Third, taking alpha is equal to 0, beta is equal to 0 in given condition, then we have alpha into u plus beta into v is equal to 0 factor belongs to w. Hence, 0 element exists in w. Fourth, by taking alpha is equal to minus 1 and beta is equal to 0 in given condition, we have alpha into u plus beta into v, which is equal to minus u belongs to w, for each u belongs to w. Hence, every element in w has its additive inverse. Now, as the elements of w are elements of v and they satisfy all remaining properties of vector space in v, so they satisfy in w also. Hence, W is a vector space, so it is a subspace of V. Next theorem. If U and W are subspaces of vector space V, then show that U intersection W is a subspace of V. Also, give an example to show that union U union W is not a subspace in general. Proof. Let U and W belongs to U intersection W. Then U and W belongs to U and U and W belongs to W, and let alpha is any scalar. Then alpha into U belongs to U and alpha into U belongs to W. Hence, U plus W belongs to U and U plus W belongs to U implies alpha U plus W belongs to U intersection W, and alpha into U belongs to U intersection W. Hence, U intersection W is a subspace of V. Now for second part, let V is equal to R square. Let U is equal to all elements of the type x, 0, where x belongs to R, and W is a set of all the types of elements 0, y, where y belongs to R. Then U and W are subspace of V. Now 1, 0 belongs to U and 0, 1 belongs to W, but 1, 0 plus 0, 1 is equal to 1, 1. Does not belongs to U union W. Hence, U union W is not a subspace of V. Thank you.